This is the question that I asked at the end of the previous part of this video lecture, and let's think about it. So again, you can decide whether a process is reversible by thinking about whether it looks like a reasonable process if the video is played backwards. So if we look at the mass on the end of the spring played backwards, it looks perfectly reasonable. If I just play a longer video of that mass on the end of the spring, it moves down and up and down and up, and the upward parts look just like the downward parts played backwards. On the other hand, the rock falling and hitting the ground looks ridiculous when played backwards. You do not ever expect the ground to just spontaneously undent itself and shoot a rock up into the air. And so process 1 is reversible and process 2 is not. We've already seen that during inelastic collisions, some of the kinetic energy of a system disappears. But where does it go? Is it destroyed? Well, something else we've just noticed about inelastic collisions is that they always change the state of the system. Could there be a connection between the change of state of the system and the disappearance of kinetic energy? Well, this is going to give us a new hypothesis. It's time for a new hypothesis, and I know I led you through a lot of hypotheses that we discarded in the last unit. Well, spoiler alert, this is a hypothesis we're going to keep. In fact, we're going to be testing and expanding on this hypothesis for pretty much the rest of the course and on into Phys 1204. So this is a biggie. So first part of the hypothesis, there's some quantity that exists which is somehow associated with the state of any system. And so if the system state changes, then the value of this quantity also changes. And we need this quantity to have the same units as kinetic energy. We're going to call this quantity internal energy. Why do we need to have the same units as kinetic energy for this? The reason is that our whole purpose here is we're trying to explain the disappearance of kinetic energy. So we're hypothesizing that when the system state changes, the kinetic energy doesn't disappear, it just turns into a different type of energy that we're calling internal energy. You may have seen the idea of potential energy earlier in your studies, and right now you might be asking whether internal energy is the same as potential energy. Have I just taken something you already know about and given it a new name, sort of like mass and inertia? Well, the short answer is no, that's not what I've done, but the long answer is that maybe I'd better give you a bit more detail. So the type of potential energy you've probably seen, if you have seen it at all, is gravitational potential energy, and it's related to the height of objects. So in other words, a ball, or rather the ball-Earth system, has more gravitational potential energy when the ball is high up than it does when the ball is low down. But note, I had to say ball-Earth system. I can only include this as internal energy for the system if all the objects involved are in the system. And we're talking about an interaction between the ball and the Earth. So this potential energy is part of the internal energy if the system includes both the ball and the Earth. But this is only one type of internal energy. There are other types of internal energy. I'm not going to go into great detail on this now because this is a topic for Unit 7, but I'll say there's potential energy, and there are types of potential energy other than gravitational. There's thermal energy, and there's source energy. If you've seen potential energy before, I hope this clarifies things a bit. If you haven't seen potential energy before, don't worry about it. I've been throwing around this word energy for a little while now, right? We've met kinetic energy and internal energy, but what is energy? You probably already know a definition for it. I'm sure you've been introduced to it as capacity to do work. Well, are you satisfied with that definition? If you're like me, you probably find it rather unsatisfying. So we're going to develop a better understanding of what energy is, but it's going to take us a long time. But here's a start. We're talking about energy as something that systems have. It's not something that just exists on its own. It's a property of systems. And systems that have energy are able to do things. They're able to accelerate things, they're able to heat things up. More generally, they're able to change the state of things. There are many experiments we can carry out to test this hypothesis, and some of them are pretty simple. Here's a particularly simple one. Take a spring, compress it with a cart, and then release it. It expands and pushes the cart away so the cart moves with some velocity. Now, replace that cart with a different inertia. One thing we know is that we'll have the same interaction with the spring, but the cart has more inertia, and so its delta V will be smaller, and so its final velocity here will be smaller. But our hypothesis tells us that if we compress the spring the same amount both times, so we're putting it into the same initial state, and then it expands, and so it ends up fully expanded, so it's in the same final state, we should have the same change in internal energy in this system. And presumably that internal energy is going to get converted into the kinetic energy of the cart. So we can measure the internal energy of the springs by measuring the kinetic energy of the cart. Well, the velocities are different if you carry out this experiment as expected. But the really important thing is that the kinetic energies are the same both times. And that tells us that we do have a picture where there's some amount of internal energy stored in the spring, and all of it is being converted into the kinetic energy of the cart. And it doesn't matter what the inertia of the cart is, we get that kinetic energy, and it's just whatever was initially stored as internal energy in the spring. We can even modify this experiment to learn other things about internal energy and extend our hypothesis. So instead of replacing the cart, let's replace the spring. Or rather, instead of using one spring, let's use two identical springs. We've just doubled the size of the spring part of our system. Well, you would expect that the cart is going to go faster with the double spring, and indeed it does. Experiment shows that very easily. But the important thing is that you double the kinetic energy. Why do you double the kinetic energy? Well, apparently using two springs doubled the internal energy of the system. And we converted all of that doubled internal energy into kinetic energy. And so that means internal energy is extensive, because when we doubled our springs, we got double the internal energy. This is a very important idea I've just been discussing, and so let's check your understanding of it. So suppose we have a piece of clay and we've thrown it at a wall, and it sticks to the wall and stops. Let's think of the system to be the clay and the wall, and from the time just before the clay hit the wall until the time just after the clay hit the wall, did the internal energy of the system increase, decrease, or stay the same?